Hello, and welcome to Fixed Effects 2. Um, Today, that 2 thing is a joke because we're going to do it in SEM stuff. And so that's sort of the 2. Okay, anyways, moving on. Um, Today, we're going to go over the fixed effects models again, but we're going to do so in the framework of an SEM model. And there's some reasons why we're going to do that. I think they're beneficial. This is an experiment. I haven't done this before, but for me, it was really personally useful. So I'm hoping that it's useful for you too. So we had talked about these various models for fixed effects, and one way we did it was the dummy variable model, where we included these alpha terms, which allowed us to control for that covariance that we had already identified in our model. There was something there that we needed to adjust for, and so we conditioned on it by including it in the model. So this is city or person or whatever nesting unit you have. Those are the alphas, right? And everybody gets some variable that denotes that particular thing: person, city, car type, whatever it is that you're trying to investigate. Doing it this way is problematic for a number of reasons. One, when we talk about logistic regression, you can't actually do it. It ends up violating the assumptions that are used to calculate the likelihood equation for maximum likelihood, and as such, it will result in error, in a biased estimate. But for the kinds of work that we do in general, often there's just not a really good way to operationalize it, because we have, 1,000 people. So that's 1,000 variables. You very quickly eat up your space. And so it's not always wrong, certainly not with the kind of general linear models that we do, but it does require some modification. And so we talked about the fixed effects estimator. And basically what the fixed effects estimator does is it takes the average stuff, and you will notice that when we take the average stuff out, when we subtract the average stuff, that this goes away. The alphas go away as and non and stuff that varies both in effect and in actual value, that also goes away. But you get this fixed effects estimator as the model that we're estimating. So it's the difference from the mean. This is the mean. This is the difference from the mean. And this coefficient represents the change from the mean and its effect on the change in y from the mean. So it changes the thing that we're doing a little bit, but it provides a whole bunch of really nice features when we're estimating fixed effects models. And so we can run and estimate this model, and we were able to isolate the effect of poverty. And the benefit to this, right? And we talked about this last week with fixed effects, is that I've controlled for all. So this is the National Longitudinal Survey of Youth data, and so I've controlled for all of the person effects, all of the things: their race, their gender, the neighborhood that they grew up in, assuming that they stayed in the same neighborhood over time, and that the effect of the neighborhood didn't change, right? And all of the other static things about them, the history of redlining in the city, everything about them that is fixed is now controlled for, and I can isolate the effects. And what we saw when we initially ran the model is that poverty and self-esteem both predicted antisocial behavior. But here it turns out that only self-esteem changes affect change in antisocial behavior. And since that's the question about what produces causal relationships, when I change, I can't change my race, but I can change my self-esteem. If I change my self-esteem, does that change my antisocial behavior? And it turns out here that the model suggests that it does. And that we see with this coefficient here is statistically significant. And so this is what we talked about last week. But we're going to take this same model and we're going to use a structural equation framework to do this. And there's a lot of reasons why. I prefer the structural equation framework to the SEM framework that or to the traditional XT reg framework, or GenMod framework, or PLM, whatever the framework is in R. Because for me, it's a very flexible framework, and it allows me to do a whole bunch of things. And there's a few tricks and there's a few details that you have to get right. And so it might not be the place where you want to start, but I think it really it gives us a lot of real benefits. First of all, it allows us to go to the hybrid model, which we're going to go to soon, very quickly and easily. It's really the best way, I think, to move to the hybrid model. It also allows for use of likelihood ratio tests to compare fixed and random effects, which you can't really do when you are running the models using the traditional approaches to fixed effects models. So we can directly compare whether our fixed and or random effects model is superior. It also is going to give us some statistics as just a standard output in the fixed effects in the SEM framework that allow us to look where we have problems that would violate the assumptions of random effects models, and we'll see that today. It allows for lag models and reciprocal effects and these complicated models. You can run instrumental variable models really easily in this, and so that's all advanced stuff that is really, really helpful when looking at longitudinal data. And if you understand how to do the basic stuff in the SEM framework, it's really quite trivial to add those additional complexities in where it's really complicated to add it in the traditional software. In fact, you have to move to different kinds of software in order to be able to do it. We can obviously integrate latent variables since this is an SEM framework, so that's really useful. It can handle missing data, not handle as in handles Messiah, but handle missing data with full information maximum likelihood, which is often a superior way to multiple imputation to deal with missingness in your data. It obviously has the same limitations as all missing analysis have, but full information maximum likelihood uses all of the observations, even if there's missing data. And then it provides a conceptual framework for understanding these models and the differences between random and fixed effects models. So this is a picture of an SEM model. This is the same model, I will note, that we ran earlier. And we're going to walk through this, and then I'll show you the code version of it, and we'll walk through that. And then we'll estimate the model, and we'll look at the output. And by the end, you'll see that we've done the exact same thing that you've already done. Alrighty, so first I will note that you can see that the data is in wide format, not long format. And I know that because it has the years here, right? So this is the wide format of the version and of the data. And so you keep that in mind. You have to have the wide format in order to do the SEM framework, the long version in order to do the XTReg or GenMod or whatever it is you're doing in R. I will give you the code actually for the SAS and the R versions of this as well. But in Stata, you have this option of drawing the picture. And I feel like this really highlights what it is. So these arrows are just regression. So this is your dependent variable. This is your Y variable. And these are your X variables. I know that they are observed variables because they are squares. Squares are actually observed variables. And so all I'm doing is regressing self 1990 and poverty 1990 on anti 1990. And if I just had this would just be a cross-sectional regression of self-esteem and poverty on antisocial behavior, right? So that's just our standard OLS regression that you walked into the class knowing how to do. This is the error term, right? This is our epsilons that we've been spending time talking about. But there's a few additional features. One, you'll note that we have multiple equations. So each year has its own equation. So we have 3 years in the data, and we have 3 equations in the data. If we had 5 years, we would have 5 equations, right? So each year gets its own equation. The other thing is we have fixed these regression coefficients to be the same across all the years. That's because we want to because that's what we did when we did the XT-reg model. The coefficients are this, you get one coefficient for self-esteem, one coefficient for poverty, not multiple coefficients for each year, right? So we were fixing those to be the same, and that's why I have the A here and the B here. What that tells Stata is that these are all constrained to be equal to one another. There is a constraint on these error terms. You can't see it here, and it doesn't show up in this, but you'll see it when I show you the code. But we've constrained the error terms to be the same too. So there's really just one error term here. And of course, that's the standard. That's what we have when we run our models. That's what we have when we run our, all of the models that we run. You get a single error term. And I told you, I promised you in this class, you can loosen them up. It's really easy to do that in the SEM version. In fact, one of the differences between the SEM version for all the models we run and the traditional versions, XT-reg or mixed or whatever it is that we're running, is that in the SEM version, by default, the errors are allowed to be independent. So each year traditionally has its own error term, but we're going to constrain it to be equal to make it equivalent to the other model that we ran previously. And then we have this creature over here, and this is our alpha. And I know it's latent because it's a circle. An oval is a latent variable. So we're going to model the alphas using a latent variable. And you see there's an arrow to this. So this as well as is regressed on these dependent variables. So alpha is a latent variable that's regressed, and I have constrained alpha to be equal to 1. There's a 1 here. Oh, it's right here. There's a 1 for all of this. And again, when you see the code, it'll be a little clear. The straight arrow is regressed on, and so this is so these are just regressed, but I constrained the coefficient to be 1. What that does is it pushes the intercepts into alpha. And when we did it last class, when we talked about the alphas, right, we can construct intercepts for each of the variables by constructing by including the alpha, right? So you get the constant term, and then you get the alpha estimate, and the combination of those two is the estimate of each one. And here, the intercept is going to get pushed into the alpha, and so that's how we end up modeling all of the alphas. The other piece here is that these alphas are allowed to correlate with each of the x variables. You see all of these terms here, and that is a very, very handy thing. It's what makes fixed effects, incidentally, different from random effects. In random effects models, just like we assume these error terms are uncorrelated with these x variables, we assume the random intercepts are uncorrelated with these x terms. And so right here, let me just get rid of the. So right here we see these arrow terms, these arrows. In random effects models, we won't have them. We'll explicitly exclude them from the model. We'll fix them to 0 because that's what the model assumes. And if we see evidence of correlation, and we will see evidence of correlation when we estimate it, because it'll give us the output for that, and we can see how these alpha terms are correlated with self-esteem and poverty. And by doing so, we'll get a sense of how much of a violation running a random effects model versus a fixed effects model would produce for us. So there's an additional benefit to that. But suffice it to say, here we have our fixed effects structural equation model. I often like pictures, but it's actually sort of easier to see what's going on here. So as I said, we had 3 regressions, right? 3 regressions, 1, 2, 3. We've constrained them to be the same. That's this at A, at B, at 1. I constrained the alphas to be 1. And then I promised you the error term is constrained to be to be the same, and that's C, right? So self is constrained at A, poverty at B, and then the error term at C. And so this is what you would type in Stata to estimate this model. In SAST, you would use proccalis, and this is what it looks like. Again, we have all of that done correctly. In Stata, by the way, latent variables have to be capitalized. So you need to capitalize it. So don't put any capital variables in your model because that causes the problem. All the variables need to be lowercase, but the latent variables need to be capitalized. The SAS does not have the same fetish around capitalization, but you see a very similar kind of model. The error terms here are allowed to be are fixed to be the same here, and so this is the proccalis method of dealing with it. Here in R, it's Levan, and Levan is a really useful package. That is my go-to package for structural equation modeling. I think it's a little better than the Stata version, and so I like Levan. It's actually what I do structural equation modeling in. Here's how you do it in, you read the table in, and then you create this object that has the following text in it, right? So here's the model. You have our alpha variable with it fixed at 1. You have the 3 different models for each year, 1990, 1992, 94, A and B, right? Same as before. We have to, because Levan does not automatically correlate the alpha with these variables. We just run a regression here. We don't care about this. We're going to ignore it. But what the regression functionally does is allow these variables to be correlated with alpha. And then here we are correlating. We are fixing the error terms to be the same across all 3 of these, and then this is the command that estimates it, and then we get the output here. So I'm happy to talk with you guys about the respective versions if you want to learn how to run it in those versions. But when we estimate it in Stata, we can get a nice picture with our coefficients. I find these a little bit difficult to read, but you will note that these coefficients, right? So the coefficient for self-esteem is the same across all 3. That's because we constrained it. The same thing for poverty because we constrained it. Obviously, these are 1. We see the correlations between alpha and that. Between alpha and the other variables. You will notice that these correlations are a little bit on the high side, suggesting that this might be where the problem is. I think it actually ends up being poverty that is the problem, not self-esteem. We'll see in a second. So this is the other traditional output that you get. So not only do you get picture output, but you get the traditional output. And I will note that these are the exact same parameters. These are the exact same parameters that we got before. There's one other thing that I want to ask you about. So let's go back to the first version that we looked at. And I want you to note one of the things we did in this version is, where are we here? One of the things we did in this version is we estimated time. So we didn't put time in our model. What happened to time? All right. The answer, of course, is that it was pushed into the constant term. So the constant, this is the constant for 1990, 2.63. This is the constant for that is added to it for 1992. So this is what, 2.7-ish kind of. And then for 1994, it's going to be 2.84, something like that. Let's see where that showed up in the. Let's see where that showed up, and here it is. Look, it showed up here. 2.63, right? We added a little bit. It's a 2.68. I'm sorry, that's the answer. And then 2.84. So if you go back and you do the math, you'll see that the time variable is still here. It's just been pushed into the constant term. And so that's the estimate for somebody with 0 self-esteem and 0 on poverty. So we have reproduced the exact same model. You might be asking yourself again, why is he doing this to me? I'm doing it because I love you. And in the future, you will benefit from having some semblance of understanding of how to articulate these models in an SEM framework. And I think that when we move to the hybrid model, it will really, really make sense. Okay, so that's the SEM version. We are going to continue to toggle back and forth between traditional formats and SEM formats. I look forward to your feedback on this. I don't know if this is adding too much to the class. Like I said, I personally find it useful, and I think that when we have some conversations about it, I hope that it becomes useful for you as well. So let's move on to another new topic that we are introducing today, and that is the logistic model. So we have been so far in this class dealing with dependent variables that are continuous, but most of the kinds of models that we're talking about here, random, certainly generalized estimating equations. We talked about the link function, and it's super easy to create to model all sorts of dependent outcomes, dependent variables with generalized estimating equations. It's built around the general linear model that we're talking about here today. But fixed effects models have logistic model and count model, although fixed effects models are often more limited than random effects models. In Stata, there's something called MEGLM, I think, which is mixed effects models in the general linear modeling framework, which allows you to do all of these same kinds of things. You can use it instead of mixed if you want. Glimix in SAS, and I forget which one it is in R. R has a couple of packages that allow you to do the same general linear modeling framework for these nested kinds of data. But today we're just going to be talking about the logistic model because I think that's complicated enough. So when we have a variable that is a 0-1 variable, we could just model them as a linear regression, and the coefficients would be interpreted as a change in the probability that y equals 1. And so it's a nice interpretation. It's just the change in the probability. The problem is the model gets wonky really soon because you can't actually go below 0 and above 1 in probability models. But regression doesn't know that. It can do whatever it wants. So you'll get negative values and values exceeding 1 when you look at the predicted values. And that tells you something is off about your model. And that's why we use the logistic regression model, because it allows us to use a linear model framework, but have it bounded by a 0-1 when we convert it back and forth across that link variable. So we talked a little bit about the link function last time, but here's the link function as it works in the logistic regression. So logistic models use a function to map the 0-1 bounded outcome variable, right, to positive and negative infinity model. And you do that with this logit function. So you take the log of whatever x is over 1 minus x. In this case, x is going to be the probability that some variable equals 1 over the probability that some variable equals 0. And this is, the odds ratio kind of thing that we're talking about here, right? So this is the logit transformation, and then the inverse logit allows us to link it right back. So we can move back and forth across the 0-1 and then the linear model, right? So this allows us to take this nonlinear function and convert it to a linear function, and then we can convert it back if we want to. And that's what we you've used this in previous classes, I'm sure. You might not have thought about moving it across between a nonlinear and a linear function, but that's essentially what you're doing. You're using this logit function to create a linear function that allows you to accurately model probabilities that are traditionally on a 0-1 scale on a negative infinity to positive infinity scale, and then and then you can get it back to the 0-1 scale as you desire. So here's the basic logistic model. It is, as I mentioned before, it's the probability that x equals 1 or y equals 1 conditioned on x's over the probability that y equals 0 conditioned on the x's. And in this when we have this as the dependent variable, this logit function, we can just estimate these as a traditional regression model. We get our logits, right? And then those logits can be transformed into odds ratios. But it allows us to keep the probabilities, which odds can be converted into probabilities, allows us to keep the probabilities bounded between 0 and 1. So if we think about the two-period logistic model, borrowing from our progression with the fixed effects model, we see here that we have our logit function that allows us to model this as a linear function. If we're comparing two time points, we take the difference between the intercepts and the difference between the time varying variables, the time invariant variables, and the alphas all cancel out. And this is the equation that we're modeling. You should be familiar with this by now. So with the two-period model, we're in a good place. We already learned this last week, and so we're doing the exact same thing. The problem is that the fixed effects models in a logistic framework don't quite work out the same way, in part because it's harder to calculate the means. When you subtract zeros and ones only from each other, the means don't work out quite the same way. And there's this additional problem, as I mentioned in the beginning, that we can't use the dummy variable method that we can use in tradition when we have continuous dependent variables, because it violates the maximum likelihood estimation assumption when the number of parameters increases in a linear function with the sample size, right? So each person in the data set gets a variable. If we have more persons in the data set, there are more variables. And for some reason, which I do not understand, so don't ask me about it, this violates an assumption of maximum likelihood. The Allison book provides a little bit of a description of that. Suffice it to say, don't use the dummy variable method with the logistic model when we're trying to run a fixed effects model. And because we can't do the mean subtraction model because of the 0-1 problem, we also, and we can't do the dummy variable model, we have to rely on something else. And it turns out there is a solution. It's called the conditional maximum likelihood model, which conditions out the alphas from the likelihood function, which is what we want to do. We want to get rid of those alphas. And we did that by subtracting the means, right? And the alpha gets subtracted out of that. And so we have the same functional advantage where we are controlling for all of the static variables when we run these conditional maximum likelihood estimators. The disadvantage of this is that everything that doesn't change in your dependent variable also gets removed. So you lose a lot of sample size when you do this. And in the example today, we'll see an example of that where a lot of the sample size goes away. So what the conditional model does is it's a little bit tedious and complicated and beyond the scope of this class to fully explore conditional maximum likelihood. But suffice it to say, we have some y sub t variable, right, measured over time. And at two different occasions it equals 1, and the other occasions it equals it. So there's 4 occasions, right? And well, I'm telling you, there's 4 occasions in this made-up data set in my head. And it's 2 zeros and 2 ones. And it turns out that the years that it is ones are years 2 and year 3. And what the conditional comparison does is it estimates the probability that those happened in years 2 and 3 rather than all of the other pairs of years, which in this case is 1 and 2, 1 and 3, 1 and 4, 2 and 4, and 3 and 4. And if you work out the math, it turns out that that's all the possible pairs in the course of 4 different pairs, right? It's because you have 1, 2, 3, 4, and then if you work it out, I hope I didn't forget one there. No, I think I got it all. Maybe, nope. Yep, I think I got it all. Anyways, you can check my math. Tell me if I'm wrong. But this conditioning gets rid of the alphas. And so that brings us back to the place where we want to be, where we are now estimating a fixed effects model with the interpretation that is the exact same interpretation conditioned on the fact that we're talking about odds ratios and logits rather than continuous outcomes. As we had when we were doing the fixed effects models with continuous data. So let's take a look at an example and make this a little bit more concrete. The panel data that we're using is the same panel data that we used before. It's the National Survey, Longitudinal Survey of Youth, measured at 5 time points. There's a poverty variable there that is measured as a 0-1 variable. It includes the other variables that we're going to look at here include age at first interview, whether the person is black or non-black, which in most cases is going to mean white, mother at the time, whether the person is a mother at the time, the teen is a mother at the time. So I guess these are all females. Whether the person is married at the time, whether they currently are in school at the time, and the hours worked in the week of the survey. So this is a variable that doesn't change over time, and age is a variable that ironically doesn't change over time either because it's age at first interview. But the others are time varying variables, and it's measured over 5 different time points. So when we estimate it in XT-Logit, which you do the same thing that you do for XT-Reg. Again, I'm sorry, I forget what it is in SAS that you use to get this. Although if you search for fixed effects SAS proc, a Logit model, it'll tell you the answer. And then there's another one. There must be something in R, but I don't know what it is off the top of my head either. Here we have the regression coefficients, and here we have the odds ratios. So let's go over to Stata and run this. So we estimate. Nope, that's the wrong one. These are the models that I ran before. You have the code for the structural equation model. Sorry, let's run this. This is our Logit model, and we first have to, because the data is wide, we have to reshape it. We reshape it into a long data set. I rename a couple variables. I do the XT set thing, and then we get the fixed effects model that we have over on the other side. Let me get rid of this. Try that again so we can see the parameters. Go away so we can see the parameters. All right, so here we are. We have mother, spouse, school, hours. And these variables are the non-changing variables. We can't put the variables that, these are the changing variables. We can't put the non-changing variables in because the model won't run with those. So here we have the changing variables. And what we see here is that that having mothers is, being a mother has a positive effect on poverty. It increases the probability of poverty. Having a spouse at the time decreases the probability of poverty. Being in school increases the probability of poverty, and certainly none of you have any knowledge of the poverty associated with school. But you will one day have an association between working hours and making more money. And so obviously more hours lowers poverty. So none of these are particularly surprising findings. But these are logits. And while at this point I have a sense of logits, I often want to convert to odds ratios, which to me are a more interpretable thing. In Stata, you can just type in, if you've previously run something, you can type in OR logit. All the applications give you some way of exponentiating those coefficients and getting the odds ratio. So being a mother increases the odds by 1.79 of being in poverty relative to not being a mother. Having a spouse essentially cuts the poverty, the probability of being in poverty or the odds of being in poverty in half. There's a complicated relationship between odds and probabilities that I don't fully grasp. I have to use calculators to do that. So I'll be careful and say odds here. Being in school increases the odds of being in poverty, and each hour worked in the previous week lowers poverty by around 2%, lowers the odds of being in poverty by around 2%. So what you see here is the ability to take what we've talked about before with traditional regression and convert it to logistic regression. And these are just the same old logistic regression parameters that you used before, but now they're embedded in this question of change over time, and we get the additional benefit of, because we're using a fixed effects framework, we are controlling for all of the things that would have resulted in confounding in our model. All of the static, unchanging things are fixed over time. By the way, I think that I got it wrong on the, I think I didn't include, these are not odds ratios. So ignore this. I will correct it when I send out the slides. All right. We just went over structural equation modeling, and for those of you using R and those of you using Stata, you can run this same model. So we'll take a look at how to do that in just a second. I will say that SAS does not have an application for logistic structural equation modeling. Levan does it perfectly well, and SAS allows you to do it, or in Stata, I'm sorry, allows you to do it in using their SEM function. So as I told you before, we had to reshape this data, which was wide into long, in order to run XT-Logit. But if we want to run structural equation modeling, we have to convert it back to wide data. So I'm just going back to the wide data. And here's the equation. This is the exact same thing that we did before, where we have a constraint on black, a constraint on mother, a constraint on spouse, a constraint on in school, a constraint on hours, and then our alphas are all constrained to 1. I have this comma logit, and you'll notice it says GSEM rather than SEM. And then I have to use that regression trick here, because with GSEM, it doesn't automatically correlate latent variables with exogenous variables. And that's just something it's not something it's not, there's not nothing you intuit, right? Like, you just have to figure out what the parameter, what the defaults are for the program. And I learned that from Paul Allison, and so I just do what he says. But this is the trick that is used to deal with that, where I'm just regressing all of these variables. It's actually all of those variables right there. I'm regressing all of them on alpha, and that allows them to be correlated with it, which is what makes our fixed effects model rather than a random effects model. And then when I estimate this, this is going to take a little bit of a second, but it'll give me the same sets of parameters that we had, and this is the regression that I ignore because I don't care about it. This is the correlation, although it does tell you a little bit about where the violations would be in this if we were running fixed effects, we were running a random effects model, and it doesn't look like there's too many. So mother at time 5 seems to be correlated, in school at 1 and 5 seems to be correlated, and then hours worked seems to be correlated a little bit with the alpha. So those would be places that would violate the assumption of exogeneity in our random effects, and we'll talk about that more next week. You're not going to, other than checking this for violations of random effects, we don't look at it here. We don't care about it. These are obviously, as in the same model before, they're all constrained to be the same across the years. So we just have to look at this one regression in order to get all of our answers. The time variable is again pushed into the coefficient and to the constant, and then we get the same parameters for, but here we can estimate, because of the framework, we can estimate non-changing variables. And so we can see the effect for black, we can see the effect for mother, we can see the effect of having a spouse, we can see the effect of being in school, increasing poverty. I'm sure you guys love that one. And then working will also decrease your poverty as well. So all of this is consistent with the other approach. There is a little bit of programming difference, and you can see that here, right? Like, so here, this is what we did in order to get the answer. We typed in this. And so if you're just running a straight fixed effects model, and that's all you're interested in doing, obviously XT-Logit would be the way to go, and certainly in Stata. This again allows us to expand because we're spelling things out in some detail. We can really expand on that. So for example, well, I'm not going to give you for example. I'm going to hold my tongue, and we are going to deal with that in the future. I believe that is enough for today, and I look forward to seeing you on Friday.